Hello everyone, my name is Fernando Pereira, and today we continue our journey through the world of tensor compilers. Now I will talk about kernel fusion, which is an optimization that we've implemented for the XNNC compiler, and then I will tell this story. So XNNC stands for Xtensa Neural Network Compiler. It's a software tool created by Cadence Design Systems. It translates AI models into optimized machine level code for tensilic extensor processors. These processors, they exist mostly within digital signal processors, like those that are used in automotive systems, in light detection applications, in consumer electronics, and such. XNNC is implemented in C++. It's a relatively big project. Today it has about 1.5 million lines of C++ code. It's implemented on top of LLVM. Currently, large parts of it are being re-implemented to incorporate MLIR as the core building block. And part of this effort happens in the Brazilian division of Cadence, and many of our graduate students have been hired by Cadence to work on that. So today there is a nice team of people in Brazil contributing to the implementation of XNNC. XNNC follows the typical architecture of Tensor compiler. It reads high-level descriptions of machine learning models, converts them into a computational graph, and then uses this computational graph to optimize programs, which will be eventually translated into binary code. In these graphs, vertices are operators. We call these operators kernels. Typical kernels are implement the layers that we find in neural networks. And the edges in the graph represent the flow of data within the many kernels that form the neural network. Sometimes we can fuse these kernels, combining multiple kernels into single operations that are available in the library of optimized functions. This talks about optimization, kernel fusion, but what's that after all? Fusion is an old loop-oriented optimization. It's really not new. It was already presented in a paper from 1971 by Allen and Koch. Frances Allen was the first woman to win the Turing Award. A lot of her accomplishments were in the domain of compilers, and John Koch also won the Turing Award some years actually before Allen did it. When they first described fusion, it was in the context of loops. We can fuse two nests of loops as long as they have the same iteration space, meaning that the trip count of the outermost loops are similar. The fused loops, they are likely to be faster for various reasons. One of these reasons is that they will have less branches per operation, but the main reason is that usually the fused loop will have more locality. It's likely to contain less cache misses, I mean. The same principles work in the context of tensor compilers. However, in this case, we don't really need to deal with the low-level loops anymore. We can work with high-level operations. That's what I meant when I talked about exploring the semantics of named operations in the previous talk. To explain how this high-level view works, let's consider a well-known operation in transformers, the single-head attention function. Single-head attention is one of the core operations in transformers, which are used to train large language models. This operation was introduced in a paper by Vaswani et al., and is perhaps one of the most important milestones in the recent history of machine learning. The attention function is relatively simple. We can see its formula in the chart, for instance. It involves two matrix multiplications plus transposition, scaling, and softmax. If we had to represent this operation as a computational graph, we would have something like this graph here, which receives as input three matrices. These are the matrices K, Q, and V. And there is also a scalar H, but we can disregard it for the moment. We can implement single-head attention very easily in a library like PyTorch. Here's the three lines implementation. So this code implements the computational graph that we see on the bottom of the figure. If we look into the first line, we see that it contains two kernels, transposition and matrix multiplication. Each kernel is like a method invoked through the PyTorch API. Something to notice is that perhaps we could replace some of these combined operations with a single fused operation. In the example, I'm assuming that we could have an operation that combined matrix multiplication with transposition of the right parameter. This operation would fuse two of the operators in our original computational graph. Fusion, in this case, is likely to be always good, for we are not really increasing the amount of data that we need to keep in memory. Before fusion, we still had to keep K and Q in memory. After fusion, these are still the matrices we need to keep in memory. So in terms of memory requirements, fusion do not change anything in this case. But we could fuse all the operations, too. In this example, we are combining all the kernels into a single kernel, which is available in the flash attention library. But now we need to keep all the matrices in memory if we want to implement this operation of single head attention as a single kernel. When I say keeping data in memory, I'm referring to the fast memory that's part of the memory hierarchy. Usually a computer architecture is organized around a hierarchy of memory. We have fast memory that's kind of very limited, and we have slow memory that bounds. And we want to keep in the fast memory the data that we touch more often. The idea is that we can fit the data in this low memory, at least most of the time in reasonable applications. However, we might only be able to fit so much data in the fast memory because the fast memory is more limited. Then, if fusion forces us to have more data resident in memory, we end up having a lot of data transfer between fast and slow memory. This is a behavior that we want to avoid because these transfers are slow. So that brings us to our first observation about fusion. This transformation usually improves performance for reasons that I will explain soon, but improvement does not happen always. We might have regressions too. And deciding which operators to fuse is a challenging problem. Sometimes by fusing some operations together, we forgo the possibility of fusing others. This last fact brings us to our third and final observation. Fusion, when seen as an optimization problem, is guided by a cost model. Static cost models are functions that try to predict program behavior based on the features of the architecture where these programs run. There are many different static cost models. For instance, here you can see different performance surfaces produced with the cost model proposed by Olivier in 2021. In this case, we are varying the size of tiling factors and plotting the predicted performance. Here are surfaces produced for similar programs, but this time using the cost model adopted in the XNNC compiler from Cadence Design Systems. This cost model is briefly discussed in this paper, the Droplet paper by Ganesh et al. From 2024. So, given a computational graph plus a cost model, we want to find a sequence of operator fusions that minimizes the cost of running this graph. This problem is difficult to solve because if we fuse two operators, then we might prevent the fusion of other operators. Also, the order in which we fuse the operators is important. The cost model usually will not be associative when applied onto fused operators. Thus, some typical approaches to find the best sequence of operator fusions will be exponential, as they evaluate all the fusion candidates exhaustively. That's the case of the algorithm proposed by Kai et al., which does backtracking to try all the fusion possibilities. They use a memoization table, like in dynamic programming, to reduce the cost of evaluating all the potential fusion sequences. A different approach was proposed in the Tensor compiler. In this case, the compiler uses an evolutionary algorithm to decide which operators to fuse. But notice that this algorithm proposed by Zhang et al. Is not guided by a static cost model. Tensor effectively runs the computational graph to measure the benefits of the transformations it carries out. Finally, there is also the fusion algorithm that is used in the XNNC compiler, which is based on the same principles that guide the minimum spanning tree algorithm of Dijkstra. In this case, operators are fused greedily until fusion becomes no longer profitable. This algorithm, now on XNNC, was published in the International Symposium on Compiler Construction last year, and that's the algorithm that I will talk about now. It essentially is a greedy algorithm guided by a cost model. We keep grouping kernels in clusters provided that we can fuse them, and at each iteration we pick the two most profitable clusters that we can fuse and combine them into a single kernel, if that's possible. Let me illustrate the approach with this very simple example here. Imagine a computational graph with 5 kernels, here A, B, C, D, and E. Assume also a cost model that assigns cost to running the kernels. This is the cost of the vertices, and it assigns costs to transferring data. This is the cost associated with the edges. So let's assume that we can fuse kernels as long as the cost of the edges that come out, if this cost is no greater than 5, for instance. That's just an example. So we have initially 5 fusion candidates, which we sort by costs. This is the cost of each edge now that we are running the first iteration of the algorithm. We pick up the most profitable edges that we can collapse, and that's AB. We assume that our library of kernels contains a fused version of A followed by B. We keep doing that, always picking the most profitable edge according to the cost model until we cannot really do any more fusions, either because they all exceed the cost threshold or because we don't have versions of that fused kernel in our library, and that's when we stop. Let me present some experimental results to show you how the algorithm behaves. We have a collection of benchmarks. We call that Bennu. It's publicly available. That consists of 90 models in the ONNX format. They all read the same image and do inference on that image. I will show you some results involving the number of cycles to run each model. So the lower, the faster the model is. These cycles come from the Xtensa simulator. These numbers are robust against statistical variations. We can choose different processors with the Xtensa simulator, and I shall be showing some numbers for the P6 DSP. And I will be comparing 5 approaches to kernel fusion, including no fusion, which amounts to no optimization. The other algorithms are DFS, which is the original algorithm used in XNNC. This is a greedy algorithm that traverses the computational graph and fuses as soon as possible, always on the first match that comes up. Then there is MST fusion, which is the algorithm that we have deployed on XNNC, and the evolutionary algorithm that we took from Apache TVM. This is a genetic algorithm. Finally, we also use the backtracking approach from Kai et al., which is an exhaustive algorithm. And here's our results. That's a lot of bars, so let's go over them slowly. First thing to notice is that operator fusion, regardless of our approach, is always beneficial. Second thing is that the new MST algorithm is almost always better than that first approach adopted in XNNC. Well, and that's the reason it's there now. Something also interesting is that the backtracking approach is not always the best algorithm. That's due to timeouts, and we shall discuss it more later. Finally, there is not really much difference between MST and the evolutionary approach, except that MST is faster most of the time. I mean, faster to run in the computer. It yields faster compilation times. Let me show you how fast. In this case, I will be reporting compilation time. Here it is. The higher the bar, the slower is the algorithm. We had a timeout of 1 hour, and backtracking met this timeout in 11 of the benchmarks. These are the largest benchmarks. The evolutionary algorithm in turn is about 30% slower than the proposed MST technique. So in the end, MST is 30% faster and yields code of similar quality. It's a bit slower than DFS, about 10%, but generates code that's 40% faster. The implementation of MST is just a bit larger than DFS's, but is much smaller than the evolutionary algorithm. And today, that's all available in Cadence's Xtensa Neural Network Compiler. And that was our story with XNNC. In the next part of this presentation, I will tell you about our story with the TVM compiler. However, before we move on, let me ask you, are there questions?